All right, so we are going to talk about enthalpy. Hey, sweet, that went away. Cool. All right, so this is something new. Never talked about it before, so hold on. Here we go. All right, so enthalpy. So here we go. Enthalpy. Del or H is defined to be the internal energy of a system plus the product of its pressure times its volume. Okay, and so what does that equation look like? Well, H is going to equal P. Oh, sorry. It's going to be energy plus PV. Okay, so all the variables in this equation are state functions. Remember, a state function was the example we talked about going from Shawano to Madison by airplane versus going by car. All of these quantities, we don't care how they change, just that they change. Okay, and so we just want to know the final point minus the end point to figure out how this works. Now, so enthalpy is a state function because energy is a state function, pressure and volume are both state functions. Okay, now again, we're going to look as a pressure volume thing, and it's the expansion or compression of gases in a cylinder. Now, when we do that, that gives us this, where work is equal to the negative pressure times the change in volume, where V equals pressure, it's either positive or zero, and the delta V is going to equal volume final minus volume initial, or the change in the volume of the system. Okay, so the units that we use for work is liters, atmospheres, and a useful conversion that we might need to know, I don't know, maybe you should pay attention to this, is that 1 liter atmosphere is 101.3 joules. Okay, so yeah, just so you know, there it is. Okay, now there's a huge assumption being done when we do these calculations, and that huge assumption is that the pressure of the system is not changing. And so if the pressure of the system changes, well, then our math gets way more complicated, and it's just not something we're going to address yet. Okay, we will eventually, but not right now. So when we do that, we can modify our equation above. So delta H, and change in enthalpy, is equal to change in energy plus pressure times the change in volume. That's under constant pressure. So recall that our equation for delta E is Q plus W, and given that W is negative P delta V, okay, we can rewrite all of this to give us a big, long, ugly looking equation. And so delta E, get my hand out of there so it doesn't glow. I'm sorry, delta H is going to equal delta E plus P delta V, delta, I forgot the delta. That's not a V, I moved. Wow. P delta V, and that's going to equal Q P with a little sub P, Q with a little sub P, plus W minus W is going to equal QP. Okay, so the result of this algebraic manipulation is that the change in enthalpy equals the heat gained, which is what QP is. So the heat gained or lost at constant pressure. So Q, right here, this is kind of a definition. So heat is QP. Sorry, there we go, that's better. Gained or lost at constant pressure. Now, this is a huge simplification for us, and it makes the math lots easier. We're going to do a simplified version of this that you're going to be just like awesome happy with later in just a little bit. Okay? So, all right. There it is. Okay, better. Sorry. Okay. Eventually I'll figure out how to do this so it'll look smoother and all of this, but I'm not there yet. All right, so like I said, this is a huge simplification for us. So we're here. And that makes the math a lot easier. So if our system gains heat, our delta H is greater than 0. And if our system loses heat, our delta H is less than 0, and that's an exothermic reaction. Okay, and so let's do a little bit of work and see if this makes sense. Okay, what is the sign of delta H in the following scenarios? If an ice cube melts. All right, so think about this. For an ice cube to melt, what has to happen? So liquid, it's less than 0 degrees Celsius. Liquid water freezes into solid water, ice. And so to melt, it has to increase in energy and increase in temperature. All right, so for an ice cube to melt, it has to take in energy. And so it takes energy in. That means that it has a positive delta H value. Okay. 1 grams of propane is burnt to yield a complete reaction. Okay, so combustion. Propane is C3H8. Okay, so this is C3H8 plus oxygen, releases CO2 and water. Okay, a lot of our homes in northern Wisconsin are heated through using propane. If you've got a big metal cylinder outside in your yard, you're burning propane to stay warm. And so it would make sense that when we burn something, we're releasing energy as heat. Okay, and so because this is a burning process, we're breaking apart the energy holding those bonds together. Burning is exothermic. And so this is an exothermic reaction. So delta H is going to be a negative value because you're losing energy. Okay, so that's the basics of enthalpy. We're going to jump into a little bit more how to use it just momentarily. Again, on the bottom of your sheet, you have questions, and so please make sure that you are using this space to write in any questions you have as you see this so that you know that I will answer them in class. So thank you. We'll talk to you soon. Bye.